Okay, we are going to sort of continue where we left off last. So yeah, I wanted to sort of start a bit of a new topic, which is semigroups, which is just a short interlude before we discuss representation theory in the context in which we use it in quantum mechanics. So semigroups. Yeah, let's just start with the definition. A strongly continuous semigroup also called a C0 semigroup, is a map phi from the non-negative real numbers into the linear operators on H, the bounded linear operators, where H is a Hilbert space. So sort of the, I don't know, what you would expect, for example, of the time evolution operator in quantum mechanics, such that firstly, phi of a sum is equal to the composition of phi of S after phi of t for S and t non-negative numbers. And secondly, so this is the semigroup property. And now the other thing is the strongly continuous bit, which is for every vector in our Hilbert space, we want the limit where S goes to t of phi S psi to equal phi t psi. So we sort of want this thing to be not a continuous map with respect to the topology we have on here, or with respect to the norm topology we have on there, but with respect to the strong topology, which is just pointwise convergence. Now you might...
One question, a semigroup is a group minus what property again?
Inverses.
Okay, no inverses.
So non-negative real numbers are a semigroup, because are also a semigroup, because like you can add them, there's a zero, but there are no negative numbers, so there are no inverses.
Yeah.
And yeah.
Is there still a notion of an identity though?
Yes, phi of 0.
Okay.
So this phi of 0 is the identity. Yeah, I guess you have to also require that. Example. Oof, yeah, that's a bit of a mouthful, but not very hard actually. Let G be a Lie group. X a manifold with a left G action. So think of G being matrices and X being Rn or something. Then you have a left action by matrices. The reason why I'm not requiring this to be a representation is because I'm also going to look at G being the real numbers and the X also being the real numbers and the action being addition, which is not linear. G invariant with a left G action and a G invariant measure. So again, think of translation or rotation. That doesn't really change the Lebesgue measure. That alpha be a one parameter subgroup. So a subgroup that can be parameterized by one parameter. Then we can define L alpha of t of some function to just be f of alpha of minus t applied to x. So for example, e.g. g is the real numbers, x is the real numbers, and alpha t applied to x is just t plus x. Then L alpha tf is just the thing that translates a function. Or the semi-group of translations, so to speak. This thing here is generally not norm-continuous. So I guess this would be on L2R. And I even have an example for that, namely exactly that action we have here. So we have the function f, define it to be 1 over square root of t if x is contained in the interval minus t over 2, and 0 otherwise. So just a function that it's like a bump somewhere. No, not a bump. Just looks like this. So for t bigger than 0. Then we have the norm of that thing. Squared is just the integral from minus t halves to t halves of 1 over t, which is 1. So yeah, the norm of f is also 1. And if we look at the translation by t, sort of the difference between the function and its translation at x, that is now a function that has somewhere the value 1 over square root of t, and somewhere the value minus 1 over square root of t, and 0 otherwise. So that would be from t halves to 3 t halves. That would be from minus t halves to t over 2, and this is otherwise. Blah, blah, blah. We see that the norm of that difference is square root of 2. It's always square root of 2. So this shows that the operator norm of L alpha t minus 1 is always, so this is, sorry, square root of 2, which is also equal to square root of 2 times the norm of f. And that means that the operator norm of that difference is always bigger than or equal to square root of 2. So it in particular can't go to 0, meaning that L alpha of t doesn't converge to L alpha of 0 as t goes to 0. At least not in operator norm, but it does converge strongly. So for each function that you plug in, that would still go to 0. Yeah, other examples generally of that type would be Rn, the group being either Rn acting by translation, or I don't know, On acting by rotation, or just the Poincare group in general. Or Galilei group, or whatever you want to plug in there. And of course, yeah, I don't know, I'm not really putting that there. You sort of might ask, okay, we have, apparently it is important that that semigroup is strongly continuous and not just continuous. Or yeah, that's a bit weird. Okay, let's say strongly continuous but not uniformly continuous, which would be the case where this thing here is true. The reason is that uniformly continuous semigroups are a bit boring. It turns out that you can prove that they all have the shape exponential of t times a for a bounded operator. But we're sort of aiming for a to be an unbounded closed operator. So we really have to look at the strongly continuous semigroups.
Yeah, I don't get the relation with the e power at still.
Yeah, that will come now.
Okay.
In a way. So this is definition / theorem. For phi such a strongly continuous semigroup, we define a closed operator, a closed unbounded operator potentially on H, as H applied to some vector xi being the one-sided limit H going to 0 of phi H xi minus xi divided by H. So the derivative, if you want, but like one-sided, where dA is just the set of xi's for which that limit exists.
This phi at xi operation is basically like any group action on a manifold, right? That's exactly what this is.
Well,
so this
it's
is
an
kind
operator.
of like the Lie derivative.
It's just a normal derivative. So that's an operator acting on that vector.
Okay. Okay.
Yeah, it will usually be something like rotation or like finite rotation or finite translation or something like that. And I mean, yeah, that we call this thing the generator. And now then that thing A is a closed operator. Called the generator of phi. Yeah, furthermore, if you remember that bit of operator calculus we did before, where you can apply arbitrary functions to closed operators, get a potentially smaller domain, but still something that is valuable, then we notice that the exponential function restricted to the spectrum of A is bounded. And phi of t is equal to the exponential function of t times A. And yeah, this is the big result of semigroup theory. And in a PDE class, you have to work towards that for quite a while. So I guess examples, yeah, like A from L to R dA to L to R, mapping a function to I times its derivative. The momentum operator generates a semigroup. Yeah, I guess I could just call it P. Semigroup given by phi t is equal to, well, okay, we could also throw in a factor of I, IXP, finite translation operators.
One question, is there any intuition? So I know that it generates something, but is there any intuition to see that it generates semigroup, like the absence of inverses or something like that?
Yeah, there is a good reason for that. Because, well, the sort of, if we look at the definition of A, it looks, yeah, I mean, it's basically this thing here. A psi is equal to the derivative, well, within the limits within which we can define it, phi times psi, right?
Yeah.
If you then sort of apply the semigroup property a bit more, you find that the derivative, not at t equals to 0, but at any other value of t, is equal to A times phi t psi, which is a differential equation. Or like this is now a solution to the differential equation dt u is equal to au, where A is an operator, u is, well, a function that maps into some Hilbert space. And yeah, this is the setting of a lot of differential equations, because this operator can still be something differential, and you can write a lot of equations that way. For example, the example that gave sort of birth to the semigroup theory is where you take your operator to be the Laplace operator. Then you get the heat equation, which by its nature is irreversible, therefore has only a semigroup associated to it.
So this is talking about some notion of irreversibility or some notion of...
Yeah, it allows for irreversibility. I didn't really state that, but I mean, this theorem just says if we have a strongly continuous semigroup, then its generator is closed. And there's a sort of converse. If I have a generator and it satisfies certain bounds, then that generator indeed generates a strongly continuous semigroup.
And the generator in this case is just the evolution generator?
The momentum operator.
The momentum operator.
Okay.
And there's sort of different bounds. So if your spectrum is sort of bounded in the positive direction or in the negative direction, then it gives rise to a semigroup that is not necessarily reversible. But when it's bounded in both real directions, then it gives you a group, basically.
No, that's exactly what my question was. Like, how do you differentiate a group and a semigroup by just looking at its generators?
Take the heat equation, for example.
Yep. So the thing is, if we look at this, the Laplace operator, if you're like look at bounded domain and stuff, has negative eigenvalues. So the spectrum is bounded in the positive direction. And that means that it generates a semigroup. But it's not bounded in the negative direction because the eigenvalues grow smaller and smaller and smaller.
And that means that you can evolve in one direction.
And that means that I can only evolve forward, so to speak.
Yeah,
and for the wave equation, this one is reversible, right?
Well, wave equation is second order in that thing. But for example, I mean, you can look at the Schrödinger equation.
And that's why we have like a ground state, like a notion of a ground state.
That's the Schrödinger equation, right?
Yeah.
So then I divide by 1/2 IH bar, and then I have this. But now notice that the Hamiltonian is self-adjoint, so it has real spectrum, and then 1/I times the Hamiltonian just has imaginary spectrum. So its spectrum is really bounded both in the positive and the negative direction. I mean, yeah.
Wait, so the Hamiltonian is purely positive? So multiplying it by, sorry?
Purely real.
I'm sorry, purely real, and therefore multiplying with 1/I is purely imaginary.
Yeah, and then this means that it's sort of bounded in the positive and the negative direction.
Yeah, I suppose, yes.
So it's a semigroup.
So it's even a group.
So it's a group.
Yeah, because you can also evolve backwards in time. Because you're the generator 1/I times H has spectrum that is both bounded in the positive and in the negative direction.
And there's nothing about absolute boundedness or something?
No.
Okay.
So basically the issue with momentum is you cannot have negative momentum. That's the issue.
No, momentum also works.
But you said momentum generates a semigroup and not a group.
No, I said it generates a semigroup. I didn't say that it doesn't also generate a group.
Okay.
But I already see that you are getting kind of impatient for real groups. So yeah, I guess that is mostly my interlude about semigroup theory, with like the one example where it's actually relevant that it's just semi. So let's go to groups.
I'm not being impatient. If there is something else you need to cover, you should.
I mean, yeah, it's basically just more of the stuff we've already talked about. So I've the same thing in more dimensions or something. Yeah.
Okay.
Doesn't matter. So yeah, it's basically I just wanted to be able to talk about generators and know that they sort of exist and have nice properties, so that we can right away apply that to our more general case that we are usually interested in. So now we're looking at representations of groups, of Lie groups on Hilbert spaces. So a strongly continuous unitary representation. Yeah, we still need it to be strongly continuous and not uniformly continuous, of a Lie group G on a Hilbert space H is a group homomorphism rho from G to the group of unitary operators on H. That is strongly continuous. Oh, sorry, that is continuous with respect to the strong operator topology. So again, think pointwise convergence. Equivalently, we have for all G and H in our group G, we have rho of GH is equal to rho of G after rho of H. Okay, should be not really a surprise. And the map G times H to H, that just maps group element G and a vector to rho of G times V is continuous. Again, that this last statement is equivalent to the strong continuous bit. This is a bit of an involved proof. We did it in Lie groups this semester, but yeah, I don't know. Yeah, I mean, that's basically the notion of representation we've had until now. Well, with the caveat that we are looking at unitary ones, and with the caveat that we are also needing some sort of continuity that is not too restrictive. One nice property, every strongly continuous unitary representation also induces a representation of the Lie algebra. Again, something that shouldn't be that surprising. Induces so the Lie algebra representation, I'm going to call that rho hat, going from the Lie algebra of G to I times S of H. Now, what is I times S of H? Well, S of H are the closed self-adjoint operators on H. And then I'm just multiplying them by I to make them not self-adjoint, but sort of anti-self-adjoint, which corresponds to the Lie algebra of the unitary operators. Again, yeah, shouldn't really be that surprising. Think of the representation of Rn on L2 Rn by translation. Then
the reason you're doing unitary everywhere is because you want to conserve norm. That's it, right?
Yep.
Okay.
Also because, yeah, I mean, in quantum mechanics, everything is unitary.
Yeah, true.
And I mean, we often want to look at compact groups. And when you're dealing with compact Lie groups, you can actually make every representation unitary. Yeah, okay, standard example, as I was saying, is we're acting on functions on Rn by translation. Then rho hat from, well, the Lie algebra of Rn is just Rn to I as L2 Rn just maps vector x to x times the momentum operator, sort of vector wise, times I, because the momentum operator is self-adjoint, and then we're multiplying by I. Yeah, I guess there's also some identification going on, but with like domains, but that doesn't really matter. Now, the thing is that we're usually not dealing with strongly continuous unitary representations per se, because everything we're looking at is looked through the lens of we don't care about phase factors. So this is the point where the phase factors come in. Srinivas, you wanted to say something? Or?
No, it's fine. I just put it on.
Or put differently, we are a priori only dealing with projective representations. So what the hell is that? Well, we define our, for H in Hilbert space, we define the projective Hilbert space PH to just be, well, can see them as the set of one-dimensional subspaces of H. Or put differently, we just say that is H without the zero vector divided by the action of complex scalars. So the elements are vectors that are non-zero, and they're equal if they differ by a multiple, called the projective Hilbert space. Associated to H. And we can lift any linear map A from H to H to PH by having, well, A times yeah, let's say A tilde times the subspace generated by V to just be the subspace generated by AV. And in that way, we can define the projective unitary group. Called U of P of H as, well, the transformations of that projective Hilbert space that arise from unitary operators. And similarly, we can, well, it's again a group, and we can sort of define its Lie algebra. And we define that to be I times SPH. And yeah, we can give them quotient topologies, whatever, and everything sort of works nicely. And now we can look at the map that maps an operator, a unitary operator on H, to the corresponding operator on the projective Hilbert space. And this map has a kernel, and that kernel is isomorphic to U1. So, well, not really surprising. If you ignore phase factors, multiplication by a phase factor is the only thing that sort of drops out. This means that we have a short exact sequence.
One more question. When you wrote it there, you wrote like CX, right? So that means states which have different norms are also mapped to each other. So for example, if it is like psi and 2 psi, they will be the same in the projective Hilbert space, right?
Yes, but that is just because usually we are looking at the normalized states. I mean, that is the same basically as saying that we just look at those states with norm 1.
No, but then in the kernel even they should appear, right? These.
No, because we are just looking at unitary operators here.
Okay. Yeah.
So we have a short exact sequence, 1, U1, UH, U, P of H, 1. So again, UH maps surjectively onto UP of H, and the kernel of that map is given by U1. And yeah, okay. So the thing is, when we are studying quantum systems, we are often working not with representations that map into UH, but a priori with representations that map into that space. So G. Just because there's like a theorem that says basically that. And now the question is, if we have such a representation of G, projective unitary representation, so a projective unitary rep, can we actually lift that to just a unitary rep on the underlying Hilbert space? On to a rep on H. So sort of, can we pull this one back one bit? And the answer is generally no.
Why do we need the pullback? I'm slightly confused.
Oh, that's just something we're interested in because we only ever study representations on vector spaces. But sort of the theorems of quantum mechanics just give us a projective representation.
Yeah.
And yeah, that's sort of the question, if we can get an object that we already know how to study.
Like we want to write down wave functions with a phase, even though that phase is not really physical. It's just a way that we like to write things down, right?
Yeah, basically.
No, but my question mainly was the idea that why can't we work on pH? Why is pH bad? Like it's
it's
good
just
enough, right?
A lot of work has gone into representations on vector spaces, so we already know how to deal with them. Like centuries of mathematical research have been done into them. And
won't there be a future where this is more developed and we can stay in the projective Hilbert space?
Oh, well, I mean, I'm telling you how to reduce the projective case to the non-projective one. So in a way, we have that.
It's all, we have that, yeah.
Okay.
I already have a nice example, I think. Can we lift? So generally, no.
We don't have that.
Well, if we go some extra steps, we can. So consider, yeah, for some reason, I always have to bring the counterexamples. Hilbert space L2 R, and then we have the group G being R2, and it acts by AB acting on an equivalence class of functions by giving us the equivalence class of the function that maps X to X by X, IAX, Fx minus B. This thing is linear in F, preserves norms. This gives us a projective unitary transformation for each A and B. And yeah, sort of the reason why this is a projective unitary representation of G is because we can basically ignore this phase factor there, because it's just a phase factor, and therefore we can ignore it. So that means that only if we ignore phase factors do the actions of A and B commute. So only then do we have A0, 0B F the same as AB F, and also the same as 0B A 0 F. Because I mean, those things obviously commute as elements of R2, so they also need to commute as elements, like as their actions also have to commute. But they only do that if we ignore phase factors. So generally, if we sort of live to the vector level, the best thing we can achieve is a map from G to UH that is not a group homomorphism, but we have a sort of similar group law. We have U V is equal to rho U rho V times some phase factor that depends on U and V. And I guess that might be the usual picture under which projective representations are introduced. I don't know, that's at least something that I've seen in some quantum mechanics classes. And I mean, sure, we can choose rho such that this thing is patchwise, is 0 locally, but we can't choose it globally. So in a way, this is an example of the geometry of the group getting the global geometry of the group getting in the way of realizing the global properties that we want. So it has something to do with homology.
Let's get into that.
Yeah. So one step in between is the realization that what I said earlier, we can't quite lift it to a representation of G on our UH, but we can lift it to a representation of a slightly bigger group. Rho to a rep of a slightly bigger group. And that's a theorem that rho be a projective unitary rep of G on pH. Then there exists an extension E of G and a unitary rep mu of E that realizes rho. What do I mean by that? I mean that if we have UH here and sort of our inclusion map, which I call gamma here, we have our rep there, our projective unitary representation there, and then we have a bigger group E, that has a representation mu. And the fact that it sort of realizes rho just means that this diagram commutes. Yeah. And when we sort of fill in the rest of that exact sequence down there, can sort of do the same up here, still get an exact sequence, and tada, we have the diagram from our group icon. Yeah, I don't know how much I'm proving, but the construction of the group is actually really funny because it's so boring. How do we define E? Well, we define E to be, well, pairs of an operator and an object in the group in UH cross G, such that, well, if we apply gamma to the operator, we get the same as when we apply rho to the element of the group. Yeah.
This is once again defining the definition. This is exactly that.
Yeah.
Like, you didn't actually explain shit to me.
Yeah, that's the thing.
Could you treat the example that you gave above and show us that it actually works?
The example, okay. Yeah, let me.
And where is the mu? Mu is the important thing, right? Like, mu is missing in this.
Mu is the thing that projects onto the first component.
So mu E equal rho G, something like that.
No, mu of the pair AG is just A.
Okay.
So let me have a look at what our example was. Can't I? Jesus. Then we define E as the group of operators, A, B, I guess, in U of L2 times R, such that for all functions in L2, we have AF is equal, well, modulo some prefactor to exp I AX fx minus b.
I just realized one thing. This looks very much like that whole principal bundle thing where.
Yes.
Like, where.
I mean, it is.
It is like you have mu A comma G is equal to A, and similarly you can have some mu dash A comma G is equal to G, right?
Yeah, so what we have, E is basically a principal U1 bundle over G.
Principal U1 bundle over G, that's what, yeah. And physicists already guessed that. I mean,
Sorry, what?
Physicists already guessed that.
Yeah, yeah, sure. I mean, phase factors, that always calls for U1. And yeah, also note that U1 here is the kernel of a group homomorphism. So another thing we could say, E is a central extension of G by U1, meaning that U1, the action of U1 actually commutes with the group operation on E, so that U1 sort of lies in the center of E. Yeah, and now we can sort of ask, when does this thing become trivial? When
You did this also when we were talking about the whole universal covering algebra things, right?
well, I mean, that's sort of what the conclusion will be.
Okay.
Yeah, we might ask ourselves, when is E equal to or isomorphic to G times U1? When is this principal U1 bundle a trivial bundle? Or when is this central extension a trivial extension? And yeah, that's something that we classify by homology. And yeah, I'm actually going to go a bit into that. But before that, shortly, the slogan or the result of this thing is we can always lift a projective unitary representation of G to a unitary one. To a unitary representation of a central extension of G by U1, i.e., we might not be able to lift it to a unitary representation of the group itself, but maybe of a slightly bigger group. And yeah, I guess.
Does this result hold true for semigroups too?
Well, semigroups usually don't admit unitary representations.
Okay.
Or if they did, you could like construct a group out of that, okay, because you can take inverses in the unitary operators, and then.
But in the QM case, we will have semigroups, right? Often, or.
In the QM case, I mean, except if you're dealing with non-Hermitian time evolution, no, not really.
Okay. Okay. Yeah, I have some questions regarding this, but we can talk about this afterwards.
Yeah, I mean, there's not much left anyway. What are your questions?
No, but those are related to my research, so it's okay if I do it later.
Yeah, okay, let's wrap this one up.
I would still like to see a more tangible treatment of the example that we just did, because we treated the example, but I kind of have the feeling like we only replaced the terms with the terms that we had in the example above. And yeah. I would like to have it to be a bit more tangible, you know? I want to see how do these manipulations work.
Yeah, the thing is, it's like when we define E to be that thing, then it's sort of not very hard to construct the things that we want to construct, but it doesn't give us real insight, right?
I don't know, because I want to see that it, I don't know, works like a group or something. That maybe it sounds a little bit stupid, but
Stan, I think what you need is you want to this trivialization that Philip is doing, right? E is equal to G cross U1. That won't be always possible.
Yeah.
So it will depend on the holonomy of the bundle, right? So the information of how you can do this will actually depend.
maybe.
Which I think Philip is going to talk about now, right?
Yeah. Okay. So first thing, which sort of follows very directly from what I've said in the homological algebra video. Well, we have to look at what possible central extensions do exist, and that thing in general is classified by the second group cohomology group of G with coefficients in U1, where G acts on U1 trivially. Okay, this thing is maybe not very easy to compute, and therefore we are going to look at some special case. Because, I mean, that's something we always do in physics, right? Lie groups are a scary beast, infinitely many things, and they don't commute. So we always treat them in terms of Lie algebras. So that's what we are doing. So ... go to Lie algebras to maybe gain some insight. Then this diagram looks like this. Dum, 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 dum. Yeah, I guess I times S H, I times S, P of H, 0, except that, I mean, I guess we can forget about the I's.
It should be IU1, right? Why IR?
Sorry, what?
What is IR exactly?
The imaginary numbers. The real numbers multiplied by I.
No, I get that, but I don't understand why the kernel is that.
Oh, that's the Lie algebra of U1.
Okay, the Lie algebra of U1 is just IR.
Yeah.
Okay.
So, yeah, I mean, I guess we have a very similar picture, and where if we look at 0 to R to SH to SPH to 0 is a central extension. Because the notion of a center also exists for Lie algebras, so we can also talk about central extensions. Central extension of, oh, that is rubbish. I want to look at the upper thing, because those are actually finite dimensional Lie algebras. Yeah, this is, yeah, I guess, again, exact.
What's that symbol?
Sorry?
What's that symbol?
A fracture G, small.
Oh, okay.
Okay, this is the central extension of G with R. And now we can ask, when is that central extension trivial? I.e., when is it equal to the direct sum of those two, where the Lie bracket just is the sum of the Lie brackets, meaning it just looks at G.
I feel like this is now going to go into some Cartan subalgebra discussion.
Well, a bit, sure. No, not Cartan. Not really, no. It's a bit simpler than that. But generally, okay, we're not looking at when is this the case, but if this is the case, then and if G is simply connected, then we can sort of lift this isomorphism to an isomorphism of the Lie groups. Then the group E is also isomorphic to G times U1, meaning that then in particular, we get not only our representation of E on H, but also of our original group G. So when do we get a unitary representation of G? Well, if our group G is simply connected and if sort of every central extension of the Lie algebra is trivial. And yeah, again, so when is this the case? And again, there's a cohomology group that covers that question, namely the second Lie algebra cohomology group of G with R. And yeah, I think it's a theorem that that thing is zero if and only if G is semi-simple, which are like the more interesting Lie algebras we care about. And this all is stated in the big theorem by Bachmann. Let G be a simply connected Lie group whose Lie algebra has trivial second cohomology, then every projective
Philip,
unitary.
I am sure what you just wrote is once again repeating the definition. Because you said if Vj is semi-simple, if G is semi-simple, which literally means it is a direct sum of like simple Lie algebras.
Yeah.
So when the question to when is not really answered again.
What question is not answered again?
When is Lie E equals G plus R, right?
Yeah, when the second cohomology group of G with coefficients in R is zero vanishes. And that's sort of a property
you said
that you can look
only
up.
happens, but that only happens when G is semi-simple, you said.
I think it happens when G is semi-simple. It may also happen for other reasons, but yeah, the semi-simple Lie algebras definitely fall into that category. So most things that we encounter in quantum mechanics do satisfy that.
Okay.
And every projective unitary rep of G can be lifted to a unitary rep. So if we now look at our favorite example of a Lie group, namely SO3, does every projective unitary representation of SO3 lift to a unitary one? No, because SO3 is not simply connected. So we have to go to its universal cover.
Yes, you too.
And that is the reason why we have to look at SU2, why we have to deal with spinors. Or I guess same holds for SO31 Lorentz
SL2C.
and SL2C. Slogan when quantizing symmetry always go for the universal cover, universal covering group.
Why isn't it more intuitive to work in projective Hilbert spaces? This is unnecessarily complicating things, isn't it? Like, or is this better?
I mean, we don't know what projective representations look like apart from this theorem. Like we have a bunch of representation theory that says like, oh, there's irreducible ones, and for like the big groups that we know, the irreducible ones are also known, and then every representation is like a direct sum of the irreducible ones and stuff like that. We don't have any of those statements for projective representations.
Okay. So we can't find rho basically. We can find mu, but we can't find rho.
We can't classify all possible things for rho, or a priori we can't classify them. Now we can, because we can just relate them to the representations of the universal covering group. Yeah, and I guess for fun, I've also written down a couple of those, e.g. real numbers for U1, spin n for SON, yeah, I guess n bigger than or equal to, sorry, strictly bigger than 2. Pin n for ON, same condition applies. SL2C for the Lorentz group. And for semi-direct product with SL2C for Poincare group.
Lorentz, it's SL2 times SL2, right?
Yeah, which is
Okay.
SL2C.
And what you're
Okay.
saying, Stan, that holds for if you complexify it, SL2C is
Okay.
like,
Yeah, and sort of a similar thing, or I mean, sorry, what I was sort of saying before, if, for example, it is not known that every central extension is trivial, then you also have to look at different central extensions, which is why, for example, when we're doing conformal field theory, it doesn't suffice just to look at the Witt algebra, because you really have to look at every central extension of the original Lie algebra that you had. And, well, it can be proven, I think we did that in AQFT, that every central extension of the Witt algebra is of the shape of some Virasoro algebra. So I guess that is the reason, even though it's not very, I guess, intuitive. Yeah. And that was also the rest of the operator theory.